Tunneling effect. Today we are going to see what is tunneling effect, means what is the barrier penetration. Tunneling effect is simple, the penetration of particle to the barrier, means particle penetration to the offered barrier is called tunneling or tunneling effect. So when particle is confined or trapped in the infinite potential, then particle cannot penetrate or cannot show this effect. But whenever particle is trapped or confined in the finite potential well, then even though the particle energy is less than the applied potential at the walls, still it can penetrate the walls and leak out into the classical forbidden region. It is known as tunneling effect or tunneling. So examples are tunneling diode, alpha decay, tunneling microscope, and at the list there are large applications of this effect. So for this we suppose consider one-dimensional potential well. So this is a one-dimensional potential well. Here one-dimensional potential well. So this is a offered potential V naught and energy of particle is less than the offered potential. So it's a barrier height and this tunneling effect. Whenever particle is incident, it seems to offer potential, but according to the quantum mechanics, there is a finite chances that particle will penetrate this offered potential and come into the classical forbidden region. So suppose we take water and pour on a filter paper. So then what happens? When water is poured on filter paper offer a potential, but still water penetrate, means overcome on this potential barrier, penetrate the walls and leak out. So water comes in the region 3. So this is region 1, 2, 3. So water comes, means penetrate the potential barrier and comes out with the slow down energy. So energy will be slow down. This is called tunneling effect. So this effect is used lot of application, likewise tunneling diode, alpha decay and tunneling microscope. So first we see the tunneling effect, how it is used in tunneling diode. So tunneling diode is invented by Isaki, so it's sometimes called as Isaki diode. So tunneling diode or Isaki diode is a semiconductor diode which gives very fast operation, that is switching like as on off button in particularly microwave frequency region by using this quantum mechanical effect, that is penetration of particle, means tunneling or tunneling effect. So in this diode, this diode is prepared by heavily doping PN junctions which has a width of hardly 10 nanometers. So because of heavily doping, so band gap broken into the Isaki diode, where n-side conduction band electron states are more or less become aligned to the p-side hole states. So in general case, so whole valence and conduction band of n side and valence and conduction band of p side are well separated, and in between these two, so there is a Fermi Fermi energy which separate these two. But because of heavily doping, so this valence conduction of n side p side come closer, and redistribution of Fermi. These electron state of n side and hole state of p side more or less become aligned. And because of this, what happen? When we apply a very small voltage, forward bias means p side positive and n side negative terminal applied, and when we apply very small voltage in IV characteristic, small voltage before operating voltage, so because of tunneling electrons, so this electron very easily tunnel to this side, and as everyone must know, as charge carrier move, conductivity start, and because of this tunneling effect by very small force applied by applied voltage, so conductivity start. This conductivity by simply tunneling of electron. So as we increase the voltage, conductivity, this current also goes on increasing. And what happen? So when we further increase voltage, then we observe that this misalignment, this mismatch alignment, so this further shifted, n side shifted more up, so misaligned, and current start decreasing. Then this is called as a particular region, this is the point, this is called negative region. And as voltage increases, current start decreasing, and when 0.3 voltage, so this is general operating voltage of a germanium diode, here and onward, so this diode acts as a normal diode, follow the normal IV characteristic of a diode. So the most important operating region for the tunnel diode is negative resistance region. This is called fast operating. This acts as an like on a button, particularly in the microwave frequencies. And when you apply the reverse biasing, then it operates as a Zener diode and follow all the characteristics. So this is about the tunneling diode. It totally works on tunneling, quantum mechanical effect, tunneling of electron of nearly more or less aligned valence conduction band. So this is the second example of tunneling effect. That is scanning tunneling electron microscope. It's again work on basic principle of tunneling. So tunneling microscope is an electron microscope that gives you three-dimensional structural image of sample with the detailing of atom by atom. In scanning tunneling electron microscope, the structure surface is studied by using stylus, and that surface structure can be surface structure information can be given by atom detailing by scanning the surface with the stylus. So stylus is simply a probe, high conducting probe which has a tip of having dimension to the diameter of an atom, and this is a sample. So this sample is scanned by the stylus. This, and here in this view it is shown that the tip is made like this, and tip at a stylus, extremely fine conducting probe, slowly scan the entire surface of the sample to give the three-dimensional image. And the distance between probe and the surface is of an atom. So we get the detailed information of the structure of the surface of any sample which is to be under test. So whenever this probe scan the sample, then what happen? This electron tunnel through the surface, electron tunnel from the surface into the tip of the probe, which gives the electric signal. Electric signal can be sensed by computer, and structure of the surface, which we get the three-dimensional image, is generated and used for further studies. So this is done by two methods. First is a fixed distance. In this method, so this probe scan entire sample which will be held at a fixed distance, from the surface of sample, and scan it. Suppose surface is like this, then probe will be held at a constant distance and it will scan it. And what happen when stylus will come to area surface like this? So distance is the distance between probe and surface is atom diameter. Then what happen when probe come to this area? Maximum number of electron tunnel through the probe and gives the electric signal. Well, when stylus come to this area, when it moves forward or backward, so here the number of tunneling electron will be less as compared to the number of tunneling electron to this place. And likewise here also number of electron will be less as probe will be held at some constant distance, and these electric signals will be sensed. Generated data from the computer can be to use as map counter to generate the 3D image. Then second method is constant current method. Constant current method. So in second method, what happened? So in second method, the probe will move, the stylus will move up and down while it's scanning the surface of sample. Probe will move up and down to maintain the tunneling of electron into it, means to maintain the constant current. So as probe come here, then whatever may be the electron tunnel through the sample surface to the stylus, then when it comes to this area, then stylus will be vertically moves down to maintain constant current, means to maintain tunneling of electron every time same. So in this way, so to maintain the constant current, the probe stylus will be moved vertically up and down, and recording the vertical movement of stylus make it possible to study the structure of surface atom by atom, and the profile of surface created from the computer generated counter map. In this way, by using the scanning tunneling microscope, we can get 3D image of structure of a surface of any sample which is to be under test by using phenomena of tunneling effect. This is the best example of tunneling effect. And next example we are going to see is alpha decay. So alpha decay is another example of a tunneling effect or tunneling. So alpha decay is a radioactive process, is a radioactive decay in which alpha particles are escape, that is tunnel from the nucleus. Escape from the nucleus is tunnel from the nucleus. So in the alpha decay, radioactive decay process, simply alpha particles are escape from the nucleus, means tunnel from the nucleus. An alpha particle contains 2 proton and 2 neutron bound together, that is 2 for helium. And when alpha particle is inside the nucleus, suppose this inside the nucleus, then associated energy with the alpha particle is 4.8 MeV, means million electron volt, and it is bounded by the nucleus of around 25 million electron volt binding energy. That is to be considered as a barrier or potential barrier for the alpha particle. So classical mechanics says it's high impossible that alpha particle will be escaped from the nucleus. But as we know, alpha is a particle, so de Broglie's wavelength is associated with it. And then quantum mechanics says there is a finite chance that alpha particle will be escaped, means tunnel from the nucleus. So this is a 4.8 million electron volt energy alpha particle is within the nucleus, and our this 25 MeV energy is considered, so binding energy is considered as a potential barrier. And what happened? During the alpha decay, radioactive decay process, so though the particle energy means alpha particle which is inside in the nucleus, which has associated wave function psi, and psi is a well-behaved wave function. So though the particle energy is less, not enough to climb up the potential or overcome this potential of 25 MeV, but it will leak out, tunnel this high potential barrier, and simply alpha particle escape from the nucleus by tunneling and come into the classical forbidden region with slowdown energy. So this is, as quantum mechanics says always, though the probability of escape of alpha particle is less, but it will definitely escape from the nucleus. So this is an also best example of tunneling effect. And likewise there are another also lot of example in day-to-day life. So likewise alpha particle, alpha decay, so emission of gamma from the nucleus is also an best example of tunneling effect. So likewise all bulbs, tube light and LEDs are also best example of tunneling effect, because in glass envelope filament is there and nearly vacuum inside the glass envelope 10 raised to minus 4 to 6 torr or millibar, and when you put on the bulb, filament will be glow and light will be tunneled through the glass envelope and come out. Still there is a vacuum maintained inside the bulb. So it's a best example of a tunneling. Then when you do the exercise, then sweating comes out, is also a best example. So our skin offers some finite potential and then it allows to come out. So it's a best refrigeration system also, cooling to maintain temperature of our body. So our body is also an example, excellent examples of tunneling, because every gland secretes some hormones, chemicals, salivas. So this is tunneling of everything. Something escape from the some structure. So it's called as a tunneling, means penetration of particle to the barrier is tunneling. So likewise if you pour the water in soil pot, some extent of water will be comes out to cool water inside it, is also a tunneling. So there are a lot of examples which gives an experience tunneling is possible, tunneling is existent. So hope from this you may understand the concept of principle of tunneling or tunneling effect, and this is the purpose of videos. So in next upcoming lecture we will see some interesting concepts. Till that, stay in home, stay safe.